Everyone. Sorry for the slight delay. I had some issues with the team software. I would like to continue today with the components on relational representation in fuzzy set systems, which is a major component of this set of lectures. And we spoke last time on how the relation in crisp set completely different from those of fuzzy sets. Remember what we discussed last time when we spoke about the 2D type of crisp set representation, when we are dealing with the usual type of relation between a variable x1 and the variable x2. X1 could be the independent variable, x2 is the dependent variable as a function of x1. We have seen that for the fuzzy logic systems, this is completely different. And I would like to recall here that what we are doing exactly in this particular context is a relation between two universes of discourses. So we have seen relation between, universes of discourses, the same universe of discourse. Here we are tackling the universe of discourses of different nature, and the outcome of the two universe of discourses is given by mu r, x1 and x2. So that's what we have seen during last lecture on Friday. So I will continue on this today to investigate further these particular aspects and to delve further into relational representation of a system. So let's look. This is for the crisp case. Consider a crisp set A1 defined on the universe x1 and another universe of discourse x2. So the Cartesian product of A1 cross A2 is the rectangular area, which is a subset of the Cartesian product space x1 and x2, defined on the usual manner, which is the entire 2D space plane containing the axes x1 and x2. So if we look at it here, so if we are designing our system within this particular set here, and this particular set here, the relation between these type of crisp sets. So we are going to end up with a certain type of representation that is going to take place within this crisp set of A1 cross A2. Remember that A1 and A2 will be the intervals of whatever function variable x1 and x2 are located so within the universes of discourse. So this is universe of discourse x2, this is universe of discourse x1, similar to what we have mentioned last time in the form of temperature and possibly the pressure within a room or temperature and the weather humidity within a particular room. And this is where most of the action is occurring. So this is the 2D level representation. So this is the Cartesian type of products in the usual case. So let me go back now to the other slide. So this is what we have seen so far in the area of crisp set system. So we would like to expand this to a more representative and a more meaningful type of representation for the system, where the action on the x1 and where the action on x2 are not occurring over an interval, but they are occurring in the form of membership functions. And we would like to see where this membership function is going to take place. So this is similar to the slide I just mentioned to you earlier, but this is the mathematical formulation of these Cartesian space that we are talking about. So this particular membership function is going to take the operation of minimum of mu ax1 and mu ax2. So this is the usual case of how we are computing the level of possibilities for these type. Again, this is not probabilistic again, so this is the possibilities for the occurrence at the same time of a membership function A and the membership function 2. So this is very similar, as your friend has mentioned last time, to the implication operator between an antecedent to a consequent. However, here, the antecedents and the consequents are occurring over two fuzzy set systems, and the consequent is going to be done in a Cartesian product of A1 cross A2. So this is the minimum type of thing. And as you have possibly suspected it, we can utilize here every type of T-norm operation that connects between fuzzy set 1 and fuzzy set 2. So if we look at it here, the minimum combination applies here because each element x1, x2 in the Cartesian product is formed by taking both elements. So what we mean by that, we would like to have the outcome of a system as an element that has x1 and x2 together. So it's like an AND operation. So as if you say that if temperature is high and if the weather is humid, so if something and is something. So we are doing the conjunction of the combination of two elements. So when we are doing the conjunction, the combination of two elements, so we are talking about an AND operation. And an AND operation, we have seen it, that it's equivalent to an intersection, that it is equivalent in the larger case to a T-norm operations. Okay, so the Cartesian product A cross B provides the region of definition of the two fuzzy sets. So this is where the region is going to be held. The region of action of, let's say, temperature and humidity are going to occur within this Cartesian product. It is a subset of the Cartesian product of the bigger universes. Remember that universe X is represented, for which A is a subset. So A is included in X, and B also is included into Y. Okay, so this is the type of relation that we are doing. So this is what we are meaning here. So let's suppose that this is the universe of discourse X1, this is the universe of discourse X2, and over X1, we have over a particular area of X1, the universe of discourse, let's say temperature hot. So this could be a hot temperature. And temperature hot on a universe of discourse given by fuzzy set system is represented by a membership function. Okay, so this is the membership function, and as you may have guessed it, it is a trapezoidal type of form. So this is the trapezoidal format of this membership function. So you can see it here. So this is the membership function over the universe of discourse X1. Okay, so by the way, all these figures are mentioned in the chapter of my textbook, which is chapter 2 of my textbook. So you can look at them at your ease. And as you can see here, no, this is actually, so let me do this. Okay, so it's here. This is the membership function. Okay, so this is membership function here of the humidity. So this could be the humidity level of a particular room. So where we would like to control the air conditioner of a room. So we have, for instance, two type of independent variables. So here it's the warmth of the room, temperature, and then humidity of the room. And look now what we have, because we have membership functions over this universe of discourse and membership function over the universe of discourse. And here we are going to obtain this particular membership function that is, it's like a pyramid which is cut from the top. So it is a pyramid that is cut from the top that is going to represent the fuzzy membership function that is pertinent to humidity and to the warmth. And look where it's going to occur. This particular fuzzy sets is going to occur over the cross product of A1 cross A2. Okay, so A1 and A2, which is the base of this type of pyramid. And the values for this particular area is going to take, values according to the pyramid at its different faces. So we have 4 faces for this particular pyramid. So this is the graphical representation of a Cartesian product using the minimum operator between two universes of discourses that are completely independent. Okay, so let me give you an example here to take it a little bit further and to talk about some other applications. So here we have spoken so far about the Cartesian product. We have spoken about the fuzzy set that is pertinent to that relationship between A1 and A2, which is a relationship that is combining, two types of fuzzy sets of different universes of discourses. And the outcome came out as this particular fuzzy membership function. So now we can extend this set of representation not only to hot, but we could have here some other type of temperature. We could have warm and humidity, and then we can have another type of pyramids without its tip. That is going to be representative of that particular representation where we have the combination of humidity and the combination of the warmth of that particular or temperature. So this is, the combination, and it gives us this particular type of representation. So that's what we wanted to talk about for this particular type of relation. So why I'm doing all of this? This is going to be very handy later on when we are going to talk about fuzzy inferencing. Fuzzy inferencing is when we have antecedents of fuzzy membership functions and the consequence of a membership function. So here we have put together the relationship for the system, and we are going to extend this thing later on to consequent. So this is for now. That's what I would like you to remember for establishing the Cartesian product and the relation between two fuzzy set systems. So now let's talk about something else that is even important here, which is known as the extension principle in the area of fuzzy logic systems. So what do we mean by extension principle? So sometimes we have, a mapping function that is mapping between a universe of discourse to another universe of discourse. So this mapping could, map, for instance, temperature into air conditioner type of behavior. And if we are able to create this particular type of mapping function, then we would like to know, given the representation of this fuzzy set, what are the representation of this fuzzy set here, y, which is the consequence, as when x is applied to a mapping f. Okay, so we would like here to see what is the mapping of a fuzzy set or a fuzzy universal discourse. So is equal to what? How can we compute it when this x is a fuzzy set system? Okay, so how to compute this particular system? So we are going to start here with the discrete type of case. Remember, discrete fuzzy sets is summation of elements of the universe of discourse, where each one of those particular discrete elements is represented by its membership function value. So for various type of element, x1, x2, and xn, we have several type of representation for each one of them. So each x1 has its not its map, but its value of possibility as membership function. And this is the collection of all of them. And as we saw, that this is not a sum number. It means that it's a collection. So all of these type of sum here are, in other forms, are a collection of these type of values. So what we are having here, so we have a fuzzy set x, A could be anything. It could be temperature, it could be humidity, it could be the look of the color of a tomato, the color of an apple. It could be any type of representation. And this representation is characterized by fuzzy logic type of representation. So the extension principle, what does it tell us? The extension principle, it's a principle, so it's like not theorem, but it's something that we apply it without having to, to demonstrate it or to prove it. It's something that is occurring there, and we, through the experience, we have able to showcase that it is always correct. So the extension principle states that the image of A in the remapping F is expressed on Y, which is the universe of discourse of the consequent, as fuzzy set B, which is given by the mapping F equal to A, and that mapping is given by mu AX1, so we don't touch the value of the mu AX1. The only thing that we are touching here is the image of X1 through this mapping. Okay, so that's what we have. So mu AX1, and then here we have the image of it as Y2, and then here the image of it as the function of Yn. However, all these values are going to be equal. So there is no change in terms of the membership function value. Okay, so where y1 is equal to fx1, y2 is equal to fx2, and yn is equal to fxn. So now you tell me that this is, I mean, fine, but sometimes we end up that the value of x1 and y1 and x2 and y2, sometimes for different values of x1 and x2, we may end up with the same value of y1 and y2. What should we do at that time? We may not be able to have mu ax1 and mu ax2 for two values that are the same. So what should we do in that particular case? So this is presuming that the mapping is one-to-one mapping, which means it's a bijective type of mapping. So for each one of the input, we have one single output for that particular entity and that particular element. So now, in case where the function is not one-to-one mapping and it is many-to-one mapping, such as y1 is equal to fx1, fx2 is equal to y2, or even further, so we can have fx1 is equal to fx2 is equal to fx3, and all of them are equal. So at that time, what we are going to do, so we are going to have those values that are the same, but then their corresponding mu b, which is on the top, is going to be the maximum of mu ax1 and mu ax2. Okay, so that's how we are resolving this particular problem when we do not have one-to-one mapping, when we have many-to-one mapping. Okay, I would like you to understand this factor, and I'm going to show it to you in a small example. Okay, so let's look at this particular example, and knowing that x squared 3 is the mapping, and as you know, this is a parabola. And then in a parabola, you know that the parabola has many-to-one mapping. So if you have values of x1 here and value of x2 here, then they have the same value of y. Okay, so that's the parabola. And then this parabola, I mean, has for the value of square root of 3, so you have the value of 0. So this is at the value of x equal to square root of 3. So at the square, so that's the origin of the function. So it's delayed by square root of 3. So let's look at this particular example. So now this is a representation of the fuzzy set system. Again, so here we are not going to do the connection between the elements. So I would like to keep it as this type of representation of these spikes. Okay, so this is the real type of representation of a number or a particular process. So this could be the membership function of a temperature within a universe of discourse between -3 and 3. Okay, and we represent it in this discrete type of representation. So this is the way that we are computing it. For -2, we have the value of 0.1. For -1, we have the value of 0.4, which is the value here. Okay, for 0, we have the value of 0.8. For 1, we have 0.9. And for 2, we have the value of 0.3. Okay, even if the system occurs between the value -3 to 3, we are ending up with this particular type of representation. So now let's look what is happening when we are doing this particular type of representation and how we compute it. So here, for these particular values, we are going to compute the y's. So this is the y universe of discourse. So this is the x universe of discourse. This is the y of the universe of discourse. As you can see, for the y universe of discourse, I mean, the type of values that the system is taking, I mean, start from the value of -3 to the value of +1. Okay, so all this particular spectrum. However, here, as you can see, for the value of -3, we don't have anything here. Okay, so first of all, we are going to apply the mapping to -2, and then we obtain the value +1. We apply the mapping to -1, so this 1 minus 3, it gives us -2. Then for 0, it gives us -3. For 1, it gives us -2. For 2, it gives us the value of 1. Note here that you have two elements which are, and this is expected, which are many-to-one. Okay, so here for 1, we have the -2. For the -1, we have the same image. This is 2, 1, and this is -2. Here we have the same type of image. So what should we do? So what we will do for the values that have 1 here, okay, So we take the maximum of these two values. So we take the maximum, this is the maximum symbol, okay, of 0.1 and 0.3. And this is what we do. 0.1 maximum, 0.3. So we take the maximum of both of them, and it gives us the value of 0.3. And then we do the same thing for -2 here and -2 here. So we have 0.4 here and 0.9 here. And then we end up with the maximum value between 0.4 and 0.9, which gives us the 0.9. So this is 0.9, this is 0.3, and the remainder is going to be 0.8 for this particular value that is -3. Okay, and we end up with this particular membership function representation for the image of this particular universal discourse. So you might ask me why we are doing this mathematical thing. The extension principle is very important. Sometimes we have a mapping, sometimes we know the antecedents in the form of a membership function, and we would like to compute what the system is going to generate when we are putting it through this mapping. This, I mean, could come in many different types of application. It could be for a sensory measure. So for a sensory measure, I mean, you may end up measuring the temperature in a fuzzy set system. And then that particular system has to go through a certain type of filtering or certain type of action in order to give it to another type of processes or another type of system. And that particular type of mapping might be expressed in this particular format or even in, I mean, other type of formats. And this is the outcome of the system, which gives us, first of all, the spectrum of the values where the system is going to be, I mean, the spectrum of the values, and also the magnitude of the outcome of the membership function. This is very useful in a number of applications, and I think one of the assignments, next assignment problem, is going to tackle the extension principle system. So here we have seen the application to a very simple case where we have the discrete representation of a fuzzy set A. Okay, so I'm going now to take this to the next level where we are going to have the representation of the system in the form of a continuous case. But before I start that, I would like to take some questions if you have any before I go to the continuous case. So again, the questions could be in the form of you write to me on the chat form, or you can ask me, I mean, through the microphone.
Hi, Professor. Yeah, I had a question concerning this one, right? So this is the extension principle, and so I'm just trying to understand if we can, how does this go hand in hand with implication? That is, if then. So mathematically, I do understand it, like, you know, how this extension is this sort of mapping between a universe of discourse X and Y. But then implication is an if-then condition. So can we have a system where we do this sort of mapping first, and then we have an implication in the next stage?
Yes, I mean, yes and no. So here what we are doing, we have in the implication, so let's do this. In the implication, you know the universe of discourse of the antecedent, and you know the universe of discourse of the consequent, okay? And the implication operator provides us with the compound aspects of the antecedent and the consequent. Here, this is not an implication. Here, this is a mapping. So the mapping is going to take the antecedent and it's going to build for us the consequent. Okay, so that's the main difference between both of them. It may look like this is an implication, but it is not an implication here. So this means that this is a mapping between the antecedent to the consequent. So the consequent in this particular case is a function of the antecedent. And this particular function is no other than this particular type of mapping. Okay? It happens that we can use, for instance, in this, I mean, particular case, once we have created the map or the consequence of the function, then you can do an implication operation between the antecedent and the consequent operators. Okay? So that's the subtle type of difference between both of them. So what we have seen earlier is an implication operation between an antecedent and the consequence. If then, if tomato is red, then it is ripe. So we know the redness, the color, and the ripeness. So there is a certain type of consequence to the cause and effect. Here we don't know the effect before we apply the mapping. So once we apply the mapping between the two universes of discourse, then yes, you can apply the implication operator for the system. Is this understood?
Yeah, it makes sense. Yeah, thank you.
Okay. Any other question, please? Okay, so if no other questions, so let me continue now, which is a little bit, little bit more delicate here when we are dealing with the continuous case for the fuzzy representation. So as you know here, this is the generalized Bell membership function. Generalized membership function, as I mentioned to you, it's one of the richest and the most, useful type of membership functions that we have seen in the area of fuzzy logic system. So there are three parameters for that particular membership function. So this first parameter, second parameter, and the third parameters, as we have seen them in the generalized Bell membership function. And I'm going to show it to you in the next slide. And what we have here, this is the membership function of the input, okay? And then we have an fx, which is going to map this input into consequence output. Okay, so in the consequence mu by here. Okay, so we would like to do this particular type of, so what is mu by that we are going to obtain through this particular mapping, So in order to do that, I would like to show it to you, in visual type of format representation. Okay, so this is the membership function of our system. This is the generalized Bell membership function here, generalized Bell membership function. Okay, so it is given by this particular format. So I did not complete the format here because I'm using, for between the interval -3 to 3. Okay, and the center is not occurring at the value of 0, so that's why it's not symmetric with respect to 0. So as you can see here, that's the membership function has its middle value. The fuzziest part of the value here is occurring at the value 2 and the value -1. But this particular membership function now is going to be mapped with this function. So this function is given by two parts. So part 1 here and part 2. Okay, so this is not a continuous function. This is not, a differentiable type of function at the value of, at the value that is going to separate between 0, so for the positive and the negative. So for the positive values, as you can see, for the positive value, we have a straight mapping. So we have a constant mapping for, the function y is equal to x from 0, -3 to 0. So this is -3 to 0 for this particular type of representation here. And then, so for the value, for the maximum value, so this is, 0 and -3. So why we are putting here -3 and 3 here? So because this is the values between -3 and 3 for this particular function. Okay, so that's where we are defining this particular type of mapping. So for values that are strictly less than 0, we have the function which is given by constant slope, which is given by x. And then for higher than value of 0, then in order to have the continuity, then we have x -1 square -1, which is a portion which is a displaced parabola, which has its center at this particular location, its center at the value of 1, and it is decayed. This particular, it is displayed with respect to the y-axis by -1. So this is the function of y is equal to fx. So what we would like to do, we would like to map this function here through this particular mapping. Okay, so we have selected this particular representation to showcase for you what might happen when we are doing it for the continuous case. So because of the case of the bijective type of function, we have to be very careful here. So there are two parts of the functions where first the function is bijective and where the function is not bijective. So the function is bijective into this area. Because we have, for each value of x, we have one single value of y. We have also, it is bijective between 2 and 3. So already we have separated the function. So this is bijective. This is bijective function. Okay, for every x, you have one single y. However, in this particular area, you can notice that for each value of the y, you end up with 2, 3 values of the x. So you have value here, you have another value here, you have another value here. So the function in this particular region is not bijective. And we have seen that when the function is not bijective, non-bijective, we have to apply the extension principle for that particular system. Let's start with the easier one. So for the bijective function, we are going to replicate the membership function of x. So in order for us to see it this way, so we are creating, the x here, and the y here, and the y is being replicated here. This is the membership function mu by. Okay, so we are tilting it in order for it to be convenient to this type of representation. So for the y, we have -3 to 3 from -3 to 3. So let's look at this particular region here, where the function is bijective. So what we are going to do, we are going to project this particular area here, the continuous, over this particular area. So we are going to do it. So here it goes this one, and then we project it according to this particular value. So as you can see here, you have -3, 0, the values that is taken between -3 and 1, and we are going to replicate it according to this x. So as you can see here, we are replicating this particular area here that is similar exactly to this particular area. Why it is exactly? Because the mapping is y equal to x. Okay? The other part, which is going to be rising faster for x. Okay, so for x is rising faster, but for y is not rising as, for x is rising faster, go from 2 to 3. It's going to be slow from 0 to 3. So that from 0 to 3, that is going to be replicated here in this particular region here. So this particular area here is going to be mapped between 0 and 3. So this is the value of 3 here for the value of y, and for the value of y, it's going to be at this particular type of location. So we are going to, merge this particular area using this. So this region here is going to be mapped according to this parabola that is going to take it faster with x, but it's going to be slower for y because it goes from 0 to 3, while for x it goes between 2 to 3. So this is going to be replicated here. So the slowness between 0 and 3 is described in this particular type of region for the membership function of y. So this could be done analytically. What is the value of y when the function is rising between 2 and 3 for the value of x? Okay, so this is for the value there the function is bijective. So we apply the fx to this particular function here, and then we end up with this particular type of representation. So this is one component. Now, the more difficult component, not difficult, but the more, intricate component is when the function is not bijective. And it is between the value of -1 to value of 2 in x. What is the value of -1 to 2? The range corresponding to 1. It's no other than -1 and 0. Okay? So between -1 and 0, the function is going to take its maximum value. What is the maximum value of the membership function of A? Is no other than the value of 1. Okay? So between the function, between the region of -1 and 0, which is not bijective, we are going to have the value of 1 for the membership function of y. Okay? And then we connect the dots. So we have here two regions, okay? So we have this particular region coming from here, this particular region coming from this particular mapping here, and then the third region, which is given by the maximum of the membership function taken within this particular area. So as you can see, between -1 and 2 for x, which is, I mean, between -1 and 2, the maximum value of the membership function is given by y. Okay, so then we connect it and we obtain this, I mean, strangely looking value of the membership function for the continuous case. Okay, so this is what I wanted to share with you here. So now let me do it in the analytical way for another component, another example, and how to extract, I mean, similar things when we are doing it analytically. So this is visually for you to understand what is a mapping means between the antecedents through a mapping to provide us the consequence. Okay, so let's look at this particular case for the continuous case. So now we are going to utilize a crisp mapping. Okay, so the crisp mapping is square root of x. So y is equal to square root of x, with x being a fuzzy number around 3. So we are going to represent the membership function of mu ax as this particular represent an x minus 1 divided by 2, 5 minus x divided by divided by 2 in this particular representation. So if x less or equal than 3, we have this blue type of representation. Okay, if x is between 3 and 5, we have this blue type of, so this is mu ax. The blue one is mu ax. Okay, now we would like to apply to this particular triangular membership function the mapping. What are we going to obtain from this mapping? So we would like to obtain mu by. Okay, so as you can see from this particular type of representation, I mean, square x for values between, I mean, for x, for positive values is going to be monotonous, and it's going to be bijective function. Okay, so bijective function. So what that means? So let's look at this particular type of representation. Okay, so b, which is given by fa, is equal by mu ax for all elements of fx. So we know that, and this is not an integral. Again, this is basically the collection in the continuous case. So if we are going to represent now what is x, x is no other than the inverse of the function which is given by fx. So this is equal to f minus 1y. So this is the inverse of the function as applied to the y universe of this course. So it is given by mu a f minus 1y. Let's look at what is this f minus y. So for all the values between 1 and 3, so the first set here, we have the function given by the inverse of the square root is given by y squared. And if we take the square roots for these particular values, so this is between, for the value of y is given between square y and square root of 3. So you can see this particular function, which is x, is equal to y squared. So if we are going to represent it in the formats of mu a f minus 1, which is going to be equal to mu b y, so this is also, we can write it as mu a of f minus 1 of y. Okay, so it is equal to mu by. Okay, mu by, which is given by y squared minus 1 divided by 2. So y squared, y squared, because here, now this in the space of y becomes equal to y squared, because we have done the inverse. Remember that it's mu a f minus 1 of y. Okay, so this is a y squared minus 1. So this is the function where it's in between the values of x 1 to to 3, and in the y axis it becomes between 1 and square root of 3. The function here, it's bijective within this particular region, it is a bijective function. Now let's look when it is between 3 and 5. Between 3 and 5 we have square root of 3 and square root of 5. Okay, and the mu by is going to be in this particular format, which is 5 minus y squared divided by 2. And also in this region, for y, it's going to be a bijective type of function. So now the mu by is going to be the maximum of the mu af minus 1y over all the values of y. So let's look at it here in this particular type of region. So we have this prescribes with this particular region. So between, for x, between 1 and 3, so between 1 and 3, you are going to, so this is the region 1 and 3 here. It's going to be bijective representation, but it's going to be squared. So between 1 and 3, it's going to give us 1 to 1.7 or some, I mean, in this particular area. So 1 to 1.7. So this particular region here, it's going to map to this particular area through this one. So this one goes here. It's going to be squared because it's a parabola, but it is not a full parabola. It's only a portion of parabola, which is bijective. Bijective, this is going to be multiplied by this, and it's going to be equal to this particular region for all this particular value. As you can see, this is spread out from 1 to 3 for 2 values. Here it's spread out between 1 to 1.7, and that's why this particular function is being given in this particular area here. Okay, so this is how we are seeing it in this particular type of region. The same thing here for this particular region here. So we have this particular region here and this particular region. Okay, again, it's a bijective one. And if we go from 3 to 6, we are going to end up from where we ended up our earlier function here to the maximum value of this particular type of value for the y, which is given by 2.4 or 2.3, which is this particular area here. Okay, so this particular so here this particular region is going to map into this particular region for this particular value for all those particular areas, and the function ends in this. So because this 5 here, look, so it's going to end up here. Although, so let me undo this, because I think this is the correct area, because this is where between 3 to 5, we end up with the 1.7 to 2.3. So this particular region is going to be this particular area. Okay, and that gives us the graphical solution for this particular analytical solution for the system. So if I ask you to compute for me what is the representation of mu by for a particular type of region, so then you will tell me that it is the combination over all y's between 1 to square root of 3, between square root of 3 and square 5 for this particular type of representation. So this is the notion of the extension principle that gives us, whether for the continuous or for the discontinuous case, the mapping between a universe of discourse to another universe of discourse. Okay, so it's a little bit tricky mathematically when the function becomes quite complex. This becomes a little bit complex, but these two examples illustrate exactly what we wanted to do, what we want to represent in this particular type of representation. Okay, let me take one question here or two during this particular part before I move to the next components of our slides. Okay. Okay, so if there are no questions, so let me continue further. Okay, so now we are going to talk about some other type of operators. So why we are talking about all this type of operators? I mean, this is going to prepare us for the next part of the fuzzy logic systems. As you know, fuzzy logic system, and I teach it, I mean, sometimes I taught fuzzy logic courses as one full course. Okay, so here I'm providing you with the main concept, with the main insights. So that's why the slides are a little bit, I mean, sometimes compressed, but I wanted to also to include as much material as possible, but I wanted also to go a little bit systematically. In some other courses, I mean, people will talk about fuzzy logic systems, so they would like immediately with the fuzzy inferencing, and I mean, I respect what they do. I mean, in order to go very quickly over fuzzy logic system, but fuzzy logic system has much more complex, I mean, type of insights, and we would like to understand all the knowledge representations that are provided to us through these particular type of knowledge-based representation. So all of these type of mapping, all of these type of operations, these type of principles are going to come handy when we are going to go to the next components of the course, which is known as fuzzy inferencing, which is to be the next module of the course, which we are going to tackle in future lectures. Okay, so let's look at this particular type of representation here. Okay, so given the relation R defined by R, so now we are defining not one membership function, but we are defining relations. Look, relations here. So what is relation? So relation could be, I mean, A implies B. Or it could be two type of antecedents. A, B implies C, and this is, I mean, the antecedent, the Cartesian product of that particular type of relation. And both of them, we have seen that they are equivalent to the minimum membership function or the T norm as in general type of representation. So here what we would like to do, we would like to extract some information out of the representation of a relation. So we have seen how we create a relation A implies B, how to create, I mean, the type of membership function here, membership function on X and membership function of Y, and how we obtain the relation in the 3D. So now we would like to do the reverse function. What are we going to represent when we have what is known as projection? So we do define the first definition here in the form of projection. And by the way, in my textbook, in the chapter 2 that I have posted in the lecture, you have many examples and more details on these particular type of slides. So the first projection is a fuzzy set that results by eliminating the second set y of xy. So when we say we are projecting a fuzzy set onto x, it means that we are taking out the y from that particular type of relation. How to do that? We go to the relationship of xy, and we take the maximum of that relationship over all the values of y. Okay, so that is known as the first projection of x onto the first projection of r onto x. Okay, so the relation on x. So this is the relation of x. So again, if we have something here, this is x, this is y, and this is the relation here. So if the relation here is denoted by this particular blobs here, so then we are going to project all these type of relation onto x by taking at every slides the maximum of that relationship out of all the y's, and we project it as a membership function into x. So it's going to provide us a projection onto x. Okay, we do the same thing. The second projection is a fuzzy set that results by eliminating the first set x. So we take x out here from the relationship, and it is given by R2. Again, this is not an integral, this is a continuous type of membership function representation, and it's going to be mu R2y over y. Okay, so mu R2y is no other than the maximum of the relationship between x and y over all the values of x. I will show it to you in the next slides how to obtain these particular values. And then the total projection is given by the first projection and then apply the second projection onto x and onto y, or it's commutative as well, the second projection and then the first projection over, I mean, we start with this one. Once we obtain the maximum over onto y here, then we take the maximum over all the values of y. Okay, so the same thing here, we take the maximum over y to give us onto x, and then we take the maximum over all x's, and it gives us what is known as the total projection. Okay, so we are going to utilize this particular type of relationship representation in a short while. Okay, so this is the type of projection. So this is projection onto y, projection onto x. So we came from a particular type of relation similar to this. We ended up with the relation here that is given by this membership function. And here onto y, it's given by this membership function. So how we construct it? So let's suppose that we have these two-dimensional membership function. Okay, so this could be, comes from an antecedent x implies y. All the representations of x onto y, and then this is the relation. So the relation here. Okay, so we take that relation. So if we are going to do it onto x, what does that mean onto x? So we go for each value of y, so we start -10. And then for -10, we take the maximum value of y, which is going to be given what is the value of minus x at this particular level. And then we go throughout the whole thing and we take the maximum value for y at this particular level. And then we end up, we found it that it is equal to 1. Okay, so that's 1. That's the element 1 here for starting at this particular level. So you can see that we are taking over all the values of x's. So here, so we take on this, so we scan it. So we start, let's say, from the value of -10 to the value of 10. So we scan it one by one by one by one, and then we take the maximum values over all x's. Okay, so here we are projecting, and then we take the maximum over all the elements. So as you can see here, so the first one is going to be this little membership function. So this little membership function, okay, and then the membership function increases, and then the membership function increases for all the value of y, and then it increases until it reaches the maximum values, which is given by okay. So then we take, and then we continue the same thing. It's going to be symmetric from the other side. So now we take the maximum out of all these membership functions. What is the maximum? The maximum is no other than this particular membership function, which is the fattest in this particular region. And it's going to give us this membership function. Okay, so what we did here, we did something quite important. So sometimes we are not provided the universes of discourse of the antecedent and the consequent, and still we would like to have some information about the element of departure for these particular type of membership functions. Okay, so what we do, we go to the relationship, because sometimes we have the relationship. The relationship is provided to us. This relationship could be provided in the form of linguistic description of a process. So now, departing from this linguistic description of a process, which could be represented in the form of this Gaussian type of representation, in the form of mathematical formulation, then we end up with this membership function. So we end up here, this is the projection onto x. We do the exact similar thing for the projection onto y, and we end up with this particular membership function of y. Okay, so this is the continuous case that we have for the projection. So let's look at the discrete case. So for the discrete case, we haven't seen yet a representation of a relation in the discrete case, but let me explain to you in the discrete case. So in the discrete case, you have x, which is given over this universe of discourse, x1, so this is x1, this is x2, this is x3. Remember that in the discrete case, we have, for when we represent the value of x's, so we have x1, we have x2, we have x3. Okay, but now we have only relations. We don't know the value of mu x. Okay, so the mu x, the mu xa, let's say a here, okay, which is going to be r1 in our particular case. So what does that mean here? So y, this could be y1, this y2. Again, this is the discrete representation. We just saw the continuous representation. So the discrete representation, so I need to explain this to you because we are going to look at this particular representation in a more adequate way, and we are going to apply more type of operation later on. Okay, so what does that mean, this relation? Okay, so you are given a relation like this. What does that mean? It means that for elements, this elements here, which is related to x1 and y1, the combination relationship, the connections that is linking between x1 and y1 is given by the value of 0, 1. This is equal to mu r of x1, x2, x1 and y1. Okay, and then the relation that is going to be done later on is going to be r, mu r of all xi and yj. Okay, so this is the membership function for the relation. So this is represented in this particular case in the form of a matrix. Okay, so what is these elements? It means that's the elements that are common to the universe of discourse of X and the universe of discourse Y at their early elements. What is this element? This element connects the first element of the universe of discourse X and the last elements of the universe of discourse Y. Okay, so their combination is provide us with the value of 6, 0.6. So there is quite a bit of connections between x1 and y6. Remember that x1, y6 is the joint type of possibility for the occurrence of that relation. So the relation is very strong in this particular level. When you have y3 and x3, it is very high for the values of x1 and y5. So this, an example, could be temperature 1, temperature 2, and temperature 3. This could be humidity 1, humidity 2, humidity 6. So the connection for the particular room at the particular time is going to be the connection between humidity y3 and x3 is equal to 1. So the correlation, not the correlation, but the possibility of occurrence between the two elements is very high. So the humidity, so this could be low humidity, and this is high temperature is going to be high. So this means that this particular level, it's high temperature, medium humidity for this particular type of elements. This particular element here, it's high temperature, very high humidity, it's a value of 0.2. So this is a representation of what we would obtain in a particular type of processes. In a particular type of processes, I mean, we are obtaining these type of things. So these could be antecedents in themselves. I mean, it could be the antecedents of a relation, or they could be an antecedent and the consequent of a relation. So now, given this particular relation that we have seen for the first time now, so we would like to extract the membership function when we are projecting the relation onto X. When we are projecting the relation onto Y, what are we going to obtain? Of course, when we are projecting onto X, we are going to end up over these three elements that are represented, that are the support of this universe of discourse. Okay, so let's look at it. What the system tells us. It tells us that you go for x1, so this is the first row, and then we take the maximum value out of the first row. What is the maximum value? The maximum value is no other than 1. That's the first element. We go to the next element, which is the second row here. We take the maximum value. Maximum value is 0.9. We go to the next element, and x3 it's giving us 1, which is given by this one. Okay, so this is coming from here, this is coming from here, and this is coming from here. Okay, so that's how we obtain this type of representation. So this is membership function of R1. We call it R1, which is the universe of discourse over X, which is the first element or the first universe of discourse on which this relation is created. We do this exact same thing. We do the projection onto X. So what we mean by we go to Y1 and we take the maximum over the first column. Maximum is equal to 0.5. Maximum here is 0.9. Maximum here is 1. Maximum the fourth column is 0.9. Maximum of the first column here is 1. And maximum of the first column here is equal to 0.6. Okay, and we end up with this particular type of membership function. So this is the transpose here because we represent it as a vector here. Okay, so the vector representation, because we are dealing with matrices, so the vectors, they are, I mean, conventionally mentioned as an entity which is a column. Okay, so now let's look at the total projection. Total projection, as we said, we could obtain it from here, RT, or from this. So we could extract it from this. So what is the RT? So we take simply the maximum 4 over X. The maximum here is equal to 1. Okay, so RT is equal to 1. RT here also is equal to 1. Okay, so it's the maximum values. Okay, so this is another example to show you what we are obtaining for the function when we are dealing with the representation in the table form or in the discrete type of representation. Okay, so let me continue with this one, and now we do the reverse operation. Okay, so we have now extracted R1, we have extracted R2. Are we able now, using another operator which is known as cylindrical extension, to reconstruct our original type of relation? I tell you no. Why? Because when you are doing the maximum, when you are doing the minimum operator for a function, then you are losing a lot of information because the maximum is going to pass through, filter out several type of items. Some of them are equal, some of them are smaller, some of them are, I mean, around the value that you are computing here. Okay, so the cylindrical extension is no other than the extension over that relation. So here again, so we are having X here, we have Y. So cylindrical extension of R1, what we do, we take the first, the membership function of R1, which we have obtained it here. Remember R1? So this is R1. This is R1. And then we are going to extend it over Y. Okay? So cylindrical extension over Y. So we take this one, so we replicate it over all elements of Y. Replication. This is the cylindrical extension over Y. Okay? Look at this particular type of relation now. We have a relation, of course. I mean, it's 3 by 6 type of matrix, which is exactly the same type of dimension of the original matrix. But look at this matrix here: 0.1, 0.2, 0.4, 0.8, 1, 0.6, and look at this matrix here: 1, 1, 1, 1, 1, 0, 9, 0, 9, 0, 9. So this type of cylindrical extension, while it's going to be very useful later on, but I would like to warn you that this cylindrical extension doesn't allow us to go back to our original type of formula, to our original type of to our original relation. So what we extract here from this particular set of slides, when we are doing projection of a particular type of relation, and then we utilize the cylindrical extension, we are not able to obtain the original type of functions. So what it means here, it means that cylindrical operation composed with projection is different than R, is not going to give us R. Okay, so this is the best example. We go the same thing here. So we take y1, so we take x1 here, so the y1, and then we replicate it over all x1s here, x1, x2, x3. So this is the element that we have obtained from this particular operation here. So this is what we have here. So we replicate it 3 times over x1, x2, and x3. Same thing here. Cylindrical extension composed with the projection of R doesn't give us back our original R. Okay, I would like you to remember this very well. Okay, so it gives us a number, it gives us a set of number, it gives us another relation. So it's going to be another relation. So this could be another type of relation, which we call it Z. But that Z is different than R, the original one. Okay, so projection and cylindrical extension doesn't build us back our original type of function, our original type of relation. Okay, so that's what I wanted to mention here. So these are 2 additional things. So let's look at here. So this is the base set of A. As you can see, the cylindrical extension of A is taking this membership function and extended over all y's. Okay. Okay. So that's what I wanted to showcase you. So if you have a question here, I will take one question before I go to the next part, which is going to be the one of the major components of the course as well, which is going to lead us to the next set of slides, which we are going to tackle, I mean, on Friday and next Monday as well. Any questions, please? Okay, so again, this material also is very well explained on the textbook, and there are some examples, and I'm going to go back to some examples related to this particular type of components later on, most probably during our next lecture. But let me talk a little bit now about compositional rule of inference and what we mean by that. What is compositional rule of inference and how important it is? So far, we have seen in the course, I mean, in the component related to fuzzy logic system, elementary definitions, elementary definition of a fuzzy set, elementary definition of a membership function, elementary definition on operations on fuzzy sets, on relations between several fuzzy sets, the notion of T-norms, the notion of T-conorms, which are the S-norms. But why, and we have seen the extension principle today as well, and I provided you an example. But why we are trying to do all of these type of things? Ultimately, we are going to utilize all these type of definition and all of this type of elementary representation and elementary type of concept into a bigger type of representation. The biggest representation is how to represent the process, which was the key of, I started these slides, 2 or 3 lectures ago, how to represent the process using a formulation in the linguistic representation. And these linguistic representation usually come from the knowledge of an expert person who provides us with an information, and this type of information could be articulated in the form of rules, okay? And these type of rules are going to have variables in themselves, and these type of variables are going to be fuzzy in nature. What we are aiming at in this particular part of this course, we are aiming at extracting knowledge, extracting information from well-structured type of rules, if-then rules, using subjective type of representation in order for us to create decision-making process. And all of this is being done without the requirements for collection of data. This is being done through experience that we are providing the system, through fuzzy relations, through linguistic representation. So this is what I would like you to understand as the bigger, goal of this particular part of fuzzy logic system. We would like to represent knowledge, but not in the form of data points, not in the form of curves, but in the forms of linguistic representation, in the forms of fuzzy logic rules. Okay, so this is very important, and we are starting now talking about the notion of rule of inference. But more than that, we would like to talk about the compositional rule of inference, what it is. Okay, a typical fuzzy logic system that is going to represent for us process that is going to be represented is going to be composed of a series of if-then rules. You have seen, of course, in the Boolean algebra, how to represent discrete mathematics, how to represent certain type of inferences, how to represent rules. But most of these type of rules, you have seen them in the form of true or false type of rules, true or type of. So they are knowledge-based, they are representation of system, but they are composed of discrete type of elements that are either true or false, or ones or zero. Okay, now we are going to expand this to speak about natural language, not natural language representation, but in the day-to-day knowledge of a certain type of representation. Remember that what I showed you in the early set of slides of this course, the first set of slides, what I mentioned about knowledge representation, the knowledge base. So we are going to look at that. So each rule, so we have now a process, and this process is no other than a collection of if-then rules. That's what it is. Okay, so we are going to see how this process and how to build this process and how to make decisions after we build this process. So we are building a model now that is based on knowledge that we gathered from experience, and this model is composed of a set of if-then rules. And once this model is built, then we can do prediction, similar to what we have seen in neural network and interconnections modeling. Each fuzzy rule is going to be a fuzzy relation. Remember, we have defined the fuzzy relation, and that fuzzy relation is going to be an if antecedent, then consequent. So we are going to have antecedent, A1 cross A2. Each one of them represents, an antecedent variable, A3. Then it's going to be a consequent here, B. Okay, so we are building if antecedent, then consequence. If, then. Okay, and these type of A1, A2, A3 are no other than type of fuzzy sets. And this is one particular type of rule. So now we have going to have a whole set of rules that are going to compose our system. So this is B1, this is Bn, for instance. Okay, so these are A1, A2, A3, and these are going to be different type of fuzzy sets in the consequence. So we are going to have the collection of all these type of elements that are going to constitute, each one of them is a relation, and this type of system is going to be the knowledge base of our model. Okay, so that's what we are going to see on Friday of this week, and what we are going to discuss next, which is going to lead us on how to build a fuzzy logic system, how to build a fuzzy process, and how to create decisions out of this fuzzy process. And all what we have seen so far has been the mathematical background of what we are going to see next. Okay, so I will take a question or two before I leave. Otherwise, I will be always happy to respond to you by email or, by communicating with me or with my TAs. Okay, so all of these type of slides are there in the websites. I have the chapter textbook, which chapter number 2, which talks about all these type of elements. And we are going to start chapter 3 of my textbook, and we are going to start the notion of compositional rule of inference before we go and talk about fuzzy logic control, fuzzy logic inferencing system, which is going to be in the next several lectures. Okay, so if you don't have any questions, I thank you for attending today's lecture, and I'll see you on Friday again. If you have any questions or anything that you need to more clarification, please feel free to email me. Thank you very much, and I'll see you on Friday.